Thank you so much for the nice introduction, Devera. So it's super exciting to talk to you guys about the work generating synthetic electronic health records in OMOP using GPT. I'm actually going to go through quite a lot of slides, so I'm going to be talking at lightning speed. All right, so why is the synthetic EHR data important? Well, the fundamental issue is that we can't share the private patient data with external collaborators. Therefore, having good synthetic data will enable or speed up certain EHR research areas, such as external validation of machine learning models or phenotype algorithm, so on and so forth. So the common approach for generating the EHR data is as follows, where the longitudinal EHR data is first converted to a data matrix using the bag-of-word approach, essentially counting the number of features in a time window. Then the GAN model is trained to generate a similar data matrix. Although this approach works pretty well, the underlying data structure doesn't capture any temporal dependencies, therefore limiting its use. Due to recent advancements in deep learning, people started operating on longitudinal EHR data directly using a combination of sequence models and GANs. This is one of the good examples. In this paper, the authors created a hierarchical model where they first predict the timestamp given what's come before, timestamp of the next visit given what's come before, and then predict the diagnosis codes based on the timestamp and the previous hidden state. Although such methods seem to have captured temporal information, it is still not sufficient because all the visits are assumed to end on the same day as the visit start date, which is not true for the inpatient visits. There's no visit type, there's no discharge type in the sequence, and in addition, the synthetic data is not ready for dissemination for use. So, we think this problem should be tackled from a different angle. Instead of focusing on models, we created a patient representation that not only retains the patient timeline, but also captures essential visit information. This representation is designed to have the demographic prompt at the beginning, followed by a bunch of visit blocks. The key innovation here is the use of so-called artificial time tokens, or ATT, to represent the time intervals in days between visits or within the inpatient visit span to preserve durations. That way, we can seamlessly convert this sequence to OMOP back and forth. So based on this idea, we proposed a framework where we first convert OMOP to a bunch of sequences using the patient representation. Then we train a generative model to learn a sequence distribution and generate new data. Next, we convert the synthetic sequences back to OMOP using the OMOP converter. And finally, we evaluate the quality of the synthetic OMOP using OHDSI tools and philosophy. So for the generative model, we use GPT due to its recent success. The key idea is to treat the patient sequences or history as if they were text documents. So at the input layer, we use concept embeddings plus the trainable positional embeddings. In the model, we use 16 transformer decoders, and we train the model using next token prediction. To generate a new sequence, we randomly draw a patient from the population and turn it into a demographic prompt and feed it into the model to autoregressively generate a sequence. So when sampling from the output distribution, there are top K and top K sampling strategies, which is essentially a hyperparameter to control the shape of the output distribution. We tested a few options such as top K equals 100 or top P equals 95%, and for each strategy, we generated 500,000 patient sequences. So because we know the pattern in the representation is always the demographic prompt followed by a bunch of visits, so we can easily convert this back to OMOP records. The most important thing here is that because we have a starting point, the year token in the demographic prompt, we also have all the time intervals embedded in the sequence. This allows us to calculate the timestamp accurately for any token in the sequence, which is how we reconstruct the patient timeline in OMOP. Okay, now we have the synthetic data. How do we know it's good? Or in other words, how do we actually measure the similarity of the two OMOP instances? So we came up with this evaluation where the synthetic data is evaluated on 3 levels. On level 1, we look at the concept distributions in different groups, such as full population or female population. On level 2, we look at the co-occurrence relationships within the synthetic data. And on level 3, we're going to run logistic regression model on synthetic cohorts. So what we are looking at here is the comparison of the concept prevalence stratified by population in rows and by domain in columns, where the x-axis represents the source data and y represents the synthetic data generated using the top P95% strategy, and each dot represent the concept in the plot. So what this shows is that the majority of the concepts are actually landed around the diagonal lines in the plot, suggesting the synthetic data agrees with the source, especially in the high frequency regions. Okay, so on level 2, we're going to compare the co-occurrence matrices of the source and synthetic OMOPs. We first construct the lifetime co-occurrence matrix and then simply calculate the KL divergence between them. We also included the lower bound and upper bound. So the lower bound was obtained by applying the same procedure shown on the left to 2 randomly drawn samples from the source. And for the upper bound, we first generated a hypothetical co-occurrence matrix by assuming independence in the source data, and then applied the same procedure to obtain the upper bound. So this is the results of the KL divergence associated with different sampling strategies, including lower bound and upper bound. So basically, the closer it is to the lower bound in the bottom left corner, the better the synthetic data. And in this case, top P95% seems to be the best strategy. Okay. On level 3, we'll test whether the synthetic data carries the same machine learning capability, meaning if we generate a synthetic cohort and run logistic regression on it, it should have a similar performance as the real data. We included 5 different cohorts that we previously used in the work called Sherbert. Not going to go through the cohort definitions in the interest of time, but the hope is that we're going to include more cohorts in the future. The more, the better. So here's the results. In each cell, we report 3 numbers: the prevalence of the positive cases, ROC AUC, and PR AUC. The second column of the table, highlighted in green, shows the ground truth metrics generated from the real data. And the other columns show the metrics corresponding to different synthetic data sets. Unfortunately, we don't have time to go through the results, but the take-home message here is that we are able to replicate the model performance using synthetic data for every single cohort. In conclusion, this is the first deep learning framework that generates longitudinal synthetic data using OMOP. Secondly, we created a patient representation that allows us to reconstruct the patient timeline without any loss of temporal information. And finally, evaluation procedures show that the synthetic data preserve the underlying characteristics of the real population. I'd like to thank my team and the collaborators for your inspiration and your support. I'd like to take any questions during the poster sessions at poster 503, and thank you very much.